Hello and welcome back to the second lecture in Chapter 2. In our first lecture, we talked about motion diagrams. Here's a good example of a motion diagram of a student walking to school. And we can tell a few important things about this motion just from looking at this diagram. We can see that here in this first part, walking at a constant speed, slows down and walks at a slower constant speed. And then in the last part, speeds up and walks at a much faster constant speed. We can tell that these speeds are different because the dots are different distances apart. As they get closer together, the object is moving slower. As they get further apart, it's moving faster. That's one way that we can represent motion. Another way is to use something called a position time graph. We put the position here on the y-axis and the time on the x-axis, and it should always be that way. Position on the y-axis, time on the x-axis. Now the same motion shown on a position time graph would look something like this. We would say that he started at a position of 0 and he walked this distance in this same amount of time. So when you get to this point right here, that corresponds to this point here on the motion diagram. And then he walks more slowly to this point, and then he walks more quickly to the ending point. So it's the same motion that's just shown in a little bit of a different form. And these graphs are very helpful to us in solving problems, which as we'll see a little bit later in the course. Let's try to take it the other way. What if we had a position time graph and you want to try to interpret what the object is actually doing? So we have something that looks like this. We really have three parts of the motion here, right? We have a section here, we have a section here, and we have a section here. So when we want to describe the motion, we want to describe what's happening in each of those three different segments. So let's look at that. At t equals 0, the beginning of time, the car is 10 kilometers to the right of some origin. It moves back towards the origin. Where does it cross the origin? Right here. Then it keeps going in that same direction until it stops. So when you get a horizontal line here, then the car stops. It stops at a position of minus 20 kilometers, which means it's 20 kilometers to the left. Then it starts moving back to the right until it gets back to the origin again. See if we can apply that to another question here. So this is a graph of an object moving along a straight line. What do you think could be a possible interpretation? Well, it's tempting to say a person walking down a steep mountain because the graph kind of looks like a mountain, right? But that's not right. Remember that this is not a graph of y versus x position. It's a graph of the y position versus time. So if we were to make this into a motion diagram, it might look something like this, where it starts up here, it's moving down in a y direction. Y is usually up and down. It's going down. So during this segment right here, it's descending straight down. Then it stops for a couple right here, and then it goes down a little bit further. All right, so we take that position time graph and we turn it into a motion diagram. And that may help us to figure out what kind of motion this could be. So when you see that, which one of these answer choices would that correspond to? If you said the elevator descending, you'd be correct. It wouldn't really be a car because it's going in a y direction. You know, hopefully it's not a car, else you drove your car off a cliff and you're falling. And so it's something going up and down. The rock that falls and bounces is going up and down, but this never goes back up. It's always going down. So it can't be that one either. So the only reasonable choice is the elevator. Okay, let's look at putting this all together. So we have two ways to represent motion in physics right now. These are really important. These together form what's called a pictorial representation and also part of a graphical representation. So as I talked about in class, one of the challenges in physics, probably the biggest challenge, is taking words in a problem and translating that into a mental image of what's really happening and then translating that into math. That's really difficult. Using motion diagrams, position time graphs, and some other tools that we're going to learn as we go through the class will help you to make that leap. A big part of problem solving involves using symbols and drawings to create representations or models that are very clear and precise. We want to move from first a verbal representation. That's what we're going to start with. Most of the time the problem is given in words, so a written or verbal statement of a problem. We want to take that and we want to first try to make a picture. That can include motion diagrams, it can include making a coordinate system, just a simple drawing, identifying symbols for different things. If possible, you want to also maybe include some graphical representations. We just have one of those so far, but we're going to have more as we go along, the position time graph. And then finally, we want to take those pictorial and graphical representations and try to turn that into math. We're not going to get to that right now, but we will soon. So, summarizing all that together, how do we draw an overall pictorial representation for a physics problem? First step is usually the motion diagram. The motion diagram is probably the most important one because it's what allows you to visualize what's literally happening. Once you have the motion diagram, determine where you want the origin to be. Remember that we just kind of make up a coordinate system. There's nobody out there that says this is where the origin has to be. It can be anywhere you want. So pick a place that seems reasonable for the problem to try to make it as easy on yourself as possible. And you'll get a feel for that as we do more and more problems. Then try to sketch the situation. Show the object at the beginning of the motion, at the end, and identify any quantities that you know and any quantities that you don't know. This does not have to be a complicated drawing, just something really simple. Again, the whole idea is just to begin the process of taking words on the page and translating that into a physical situation that you can understand. Next, once you've got your sketch, you want to define symbols. So you want to have a separate symbol representing quantities like position, velocity, acceleration, time. Anything that you're going to use later in the math needs to be defined on the sketch. If you know them, you can put the numbers with them. If you don't know them, just leave it blank. Just say equals question mark. But you still want to define what it means. Then take all this information and make a table. So what you know or what you don't know. You want to have the known information and the unknown information. And then this will help you start figuring out how to put all this together to solve for what you need to solve for. So then in general, how do we solve problems in physics? That's what we're building up to here in this first week. The pictorial and the graphical representation are a good first step, but they're not the whole thing. We'll get to pretty soon working with some math too, but you don't want to jump into that right away. You want to get a good picture in your head and on paper of what's happening before you try to do any math. So the first step in our problem-solving strategy that we're going to use throughout the whole year is to model. That means to try to simplify the situation as much as you can. So for example, in a mechanics problem or kinematics like we will be doing soon, we often represent the object as a particle. We kind of ignore the size and the shape, whether it's big or small or whatever. That's typically the model. It's called the particle model, and that's the main one we're going to use right now. Then you want to visualize the situation. This is where people who are expert problem solvers and are really good at physics put in most of their effort. Beginning students always want to skip this step because they think it's unimportant. They want to go straight to the math. But figuring out how to use those equations, that's hard. And making a visual representation of what's happening in the problem will really help you figure out how to use the math. So I strongly encourage you, do not skip this step. Draw the pictorial representation. We talked about how to do that already. Use a graph if it's appropriate. Right now, a position time graph would be useful. We're going to add some more in later. You can go back and forth between these multiple ways to represent the problem, and each one tells you a little bit different type of information about what's happening. And only after you've really visualized what's happening, you understand what's happening, you have defined all your variables, you've labeled everything, then do you want to apply any mathematical models and mathematical tools that we have. And then at the end, you always want to come back and say, does your result make sense? Is it believable? Does it have the right units? Is it plausible? So for example, if we're calculating, say, a person running and you get that they were running at 90 miles per hour. Now, you probably did something wrong, right? People can't run at 90 miles per hour. If you're talking about a race car, then maybe that's reasonable, but it's not reasonable for a person. So we try to have problems that model real life. So if you get something that's just off the rails and doesn't make any sense to you, then probably you did something wrong. So let's look at putting all this together. We're not going to actually solve this problem. We're just going to make the visual representation for now, just using those first two steps. So this is a typical physics problem. A small rocket, such as those used for meteorological measurements, is launched vertically with an acceleration of 30 meters per second, and then it runs out of fuel 30 seconds later. What is its maximum altitude? So maximum altitude is how high up does it go. So we need to think about this a little bit, right? What happens? Let's make a visual model of what's going on. So the rocket goes up, right? When it runs out of fuel, does it immediately start falling down? No, we know that. It's already going up really quickly. So it keeps going up, but it starts slowing down until it eventually reaches its maximum altitude. So we've got really two parts of this motion. We have one part where the rocket is going up, right, until it runs out of fuel. And then we have a second part where it goes up further until it reaches its maximum altitude. So we've really got to break this problem into two sections. And when we apply mathematics to this, we would have to break that into two sections as well. If we want to draw a visual representation, it might look something like this, right? When the rocket is going up and it has plenty of fuel, it's accelerating upward, meaning it's speeding up. When it gets to this point, it runs out of fuel, and what happens during that time? It starts slowing down. Its acceleration is pointing downward because it's slowing down. We'll talk more and more about acceleration as we go along, but acceleration measures how the velocity is changing. Again, just a quick representation showing the variables. At the bottom, it's at a height which we'll call y0 because that's the initial height. It has an initial velocity in the y direction. We'll call that v0y. Again, initial velocity in the y direction. t0, initial time. We've got an initial acceleration here during that first time segment. Then, when it reaches the part where the rocket shut off, we have different values. We're now above the ground. We have a different height. We have a different velocity. It's a different time. So we want to give those different symbols. Then when it keeps going up, it has a different acceleration. And finally, it reaches a final height, a final velocity, and a final time. We want to identify everything that we possibly know. So at the beginning, it starts at the ground. So let's make that the origin of a coordinate system, which we've shown here, which means that our initial height is 0. It starts on the ground from rest, so the initial velocity is 0. And we're going to set our time to start there when it takes off. So all three of those are 0. Now we also know that the rockets are fired for 30 seconds. That gives us our second time. We don't know its velocity here in the middle point, but we do know the velocity at the end because when it reaches its maximum altitude, what does it do momentarily at the top? It stops. It's going to turn around. It has to stop and then turn around. So we know that it's 0 at the top. And we know what this initial acceleration was because that was also given in the problem. And what we want to find here is the maximum height, which is represented by y2. So this would be the first step in the problem. Once we've identified all this, then it becomes a lot easier to take this information and figure out what equations we need to use to actually solve for y2. If you try to jump right into just looking at a bunch of equations and picking out the right one, you're probably going to fail at that because this is a complicated situation. Making this picture really helps you to visualize it. So in class tomorrow, we're going to spend most of our time working on making some visual representations of different types of motion.